Hi everyone, welcome back to the channel. We have Precast Concrete Design Lifting Course episode 3 for you. Just before that starts, I'm going to show you a nice little video that the guys in Banner were very good to give me for this course, and iDrone.ie shot the footage. So it's of the record-breaking 50-meter long bridge beams, W19s, that Banner manufactured for the N22 Macroom bypass. The beams were manufactured for John Civils and John Craddock's, and they were designed in combination with JB Barry. They're a fantastic feat of engineering, to be fair. 50 metres long, 155 tonnes, 2.5 metres deep. There were 7 of them manufactured and installed, I think, over 2 days for this bridge. You can see here them coming up through the town of Burr, and whatever about the manufacturing of them, just the logistics and getting them to site. You can see from this footage, it's extraordinary stuff. I'm going to stop talking here and just let you watch it and enjoy it. So you can see here the beam just getting through Burr town, and I think the guys said that they're nearly maxed out with 50 metres, or else some of them houses, shops are going to have to come down. You can just see it squeezing through. So on site, you can see the beams were offloaded onto trestles, just saved on craneage. The beams could be brought down, left onto trestles, and then popped into place. The lifting itself is lifting strands, 8 number point lift. A couple of photos of the beams going in the finished bridge. Strand lifters will be discussed by Matt in next week's lecture, so one to stay tuned for. Okay, thanks for watching, guys.
So welcome to the third module, third lecture in this precast lifting course. In this module, we'll be continuing to focus on the lifting capacities and on determining the capacity of lifting pins due to shear. So last week we looked at the capacity of lifting pins due to tension, and one before that we looked at calculating the demand. So this is probably on a par in terms of the technical side of things compared to last week. So lecture 2 and 3 are probably the most technical lectures in this course, and we're kind of at the crest of the hill here now, and the final 3 lectures are less technically intensive. So quick admin slide before we start. I mean, it's the same as each week. Microphones off to prevent any disturbance. We'll have time at the end for Q&A. The course will be recorded and the handouts will be sent out after each lecture. Any technical queries, you can see my email there, and I'll try to respond to them as best I can. Summary of the course outline. Looking at we're now moving on to the next module, which continues to focus on lifting capacities. Before getting into this, we'll have a quick recap, like we did previous week, of last week's module, where we discussed the lifting capacities due to tension failure modes, and we'll have some questions at the end. So after we have our recap of last week's module, we'll continue with some technical discussions on lifting capacities in relation to shear this time. And then following that, I'll speak about how to account for situations where tension and shear act at the same time, and how to account for this interaction. So typical slab lifting, for example, with your chain angles at 30 degrees, you're going to have tension forces and shear forces on your lifters, and they're both trying to the same piece of concrete is essentially trying to resist both sets of forces. So there's an interaction to be accounted for there. We'll finish up with looking at some supplementary reinforcement that you can use in order to help resist the tension and shear forces. and we'll follow that with a full worked example, basically continuing on from the simple slab that we started with in lecture 1. We'll now check that simple slab in terms of its capacity in tension and shear. So last week we focused on capacities of lifters due to tension failure modes. We took the general capacity formula, broke it down into its individual components for each failure mode. And for steel failures, we showed that the rated capacity of the lifter that you typically find in the brochures is acceptable and complies with the approach taken by the Eurocode. There are 4 concrete failure modes in tension: concrete cone failure, concrete pull-out failure, blowout failure, and concrete splitting failure. The first 3 we kind of showed formulas with quite a number of factors in it. As I said, they're all fairly well explained in the slides and in the code itself. And then the final one was concrete splitting failure, which generally can be satisfied with minimum reinforcement. Way back in module 1, we spoke about the different codes that are used. We had a general Eurocode for fastenings in concrete, and we had one more specific to precast lifting, with a lot of over and back between the two. And one question that was raised to me last week on that was the formula for splitting failure. So these next 2 slides are essentially from lecture 2 with an amendment. The formula for splitting failure is provided in the general Eurocode for fastenings in concrete 192-4. And that, in terms of the partial safety factors, we need to ensure that when we're doing precast lifting, that we include the precast lifting and handling safety factor from CEN 15728. Typically, the partial factor for reinforcing bar is 1.15. But then in addition to that, according to CEN 15728, we need to add in another factor, and for steel rebar, it's 1.8. And that essentially is to conform with the older way of designing with a global factor of safety of between 2.5 to 3, to make sure that we conform to that. So the second slide then is a revision of the formula that we presented and the values. So in this gamma SRE, so that's your reinforcement partial material factor, and that has 2 components in terms of lifting design. So it's got your 1.15 for the material, and you've got your 1.8 for the lifting and handling, and that gives you a total value of 2.07. So it increases the amount of steel required to resist splitting. And in this particular scenario, where we looked at a 32-ton lifter, the biggest in the range, you need 662 millimeters squared, which is the equivalent of about 6 B12s kind of centered around the lifter uniformly. So again, it's not a huge increase. Last week, I think we said we needed 4. Now it goes to 6. And this is for the biggest lifter in the catalog. So again, it's not a huge amount of reinforcement. Generally, if you're using the biggest lifter in the catalog, it's a big unit, which probably has large amount of steel in there anyway, and you can rely on that steel for this check. So generally, this check is always going to be satisfied still. In terms of lifting pins, I've just slide up again. I've showed this slide every week now. So again, we've got the forged foot that gets cast into the concrete. The foot is the primary load transfer mechanism for tension forces. And for the shear forces, which we're talking about this week, direct contact is typically made between the clutch in the dome and bears against the concrete there. Probably quite difficult to theoretically put a number to exactly what's going on in this area. So we bring everything back to what the actual lifter is doing in terms of shear. So it is the area of concrete in contact with the lifter sufficient? Is the steel section of the lifter sufficient? And that approach is applicable to all types of lifting components in shear. When we look at shear failure modes, we take the same approach. So we check the steel failure modes, which is essentially the shear failure of the head or the pin of the socket. See here on the left, these two examples where the head can shear off or the socket can shear off. When it comes to lifting pins, it's generally the shank diameter that's the most critical. When it comes to the likes of sockets, what you will find is that in nearly all circumstances, that when you've got, like, for example, a wavy tail, that when you check the shear through all the components, through the actual socket portion, through the rebar portion, that it's the actual rebar portion that governs. So as a rule of thumb, it's always good to use the diameter of the rebar as your in your design capacity formulas. So we've got 3 concrete failure modes then to be considered. We've got pry-out failure mode, which can be seen here, and comes from the calculations when we get into them. It's similar to like half a concrete cone failure that we would have seen last week. The next one, and probably the one that governs the most, is concrete edge failure. So we've got a couple of examples of concrete edge failure here in the likes of a wall. Down here in the bottom left, we've got examples of an edge failure in a slab. And actually this one here on the very left is an example of if you're like tilting a panel. So you got edge failure when you're trying to tilt that panel. And then the final concrete failure mode in shear is local concrete crushing, where basically the shaft of the lifting pin bears against the concrete locally and crushes the concrete, hence preventing any further shear transfer. So this kind of dark gray area here gets crushed, and what happens then is it's no longer acting in shear. You now have a lever arm, and the pin will bend, and because of obviously the diameter of the pins, it doesn't have great bending resistance, so that'll lead to failure. And this is particularly important for lifting, because when you're demolding, your concrete strength is going to be quite low. So you got a low resistance in the concrete strength, and the diameter, the surface area in contact with the concrete from the shear force is quite small. It's the diameter of the pin. So you got a high concentration of force on a low strength concrete. So it's always good to check that one as well. For pry-out failure, we can prevent it by increasing the length of the insert. It's independent of edges, so I mean that's increase the concrete strength or increase the edges. Edge failure, we can add additional reinforcement, and we'll talk about that at the end of this lecture. And when you're tilting, you should always add in additional reinforcement around your lifter for tilting, and a number of different brochures will have different scenarios, but it's essentially some kind of form of a cranked U-bar similar to that gets wrapped around in hard contact with the lifter. So we'll go through the explicit formula to how you can actually work that out a little bit later on. So for concrete edge failure, so I'm going to take a similar approach like I did last week. I'm not going to explain every single factor in these formulas. I'll cover the main ones and try and explain how the concrete or the pin behaves when it comes to these different failure modes in diagrams and stuff like that. So let's try to keep it more less theoretical, less numbers, and just get the concepts across. So for concrete edge failure, when we look at the diagrams, we can see that the failure line propagates at an angle of about 35 degrees, similar to concrete cone failure last week. When we can generate an equivalent rectangle breakout area. So it's the top surface coming out to the edge, side edge here, and it's 1.5 times your edge distance. It's similar to what we would have had last week. So in order to have, I suppose, the full area of concrete available, we need to have concrete 1.5 times the edge distance to the left, to the right, and I suppose into the concrete. This image here on the right, this side section, kind of explains that this kind of wedge of concrete. So your shear force is being applied at or very close to the surface from your lifting device, and therefore your first point of contact or your highest concentration of force is at the surface, and it's going to try and pop off this wedge of concrete if the concrete doesn't have enough strength. So as can be seen from the formula, the resistance to the concrete edge failure is a function of similar parameters which we saw before. It's also a function of the diameter of the lifting pin, which kind of makes sense. Like I said previously, the smaller the pin diameter, the smaller the contact area, and thus you got a higher concentration of stress. So when we look at the, I suppose, the reduction factor that we have to take account of in order to, I suppose, calculate this, we have a few scenarios presented here. So it's all a function of the edge distance C1, and which is the distance parallel to the direction of force. So you can see in all these diagrams, the force V is kind of pushing down to the bottom left, and it's that edge towards that edge is your critical distance C1. This image at the top here is the scenario where you have no area reduction factor. You have the full surface area available. We can achieve the full distance 1.5 times C1 to the left of the lifter, 1.5 times C1 to the right, and 1.5 times C1 into the depth. This image on the left is, say, for example, if we're in a corner where we have one edge less than 1.5 times C1 into the corner. So we just need to take account of that so that we don't have the full area available. So that's where a reduction comes in. Similarly, on the right-hand side, again, it's a general diagram showing two contact points, two castings. For lifting, typically you wouldn't be that close. Some situations you might be, but you just got to bear that in mind that the spacing between the lifters, only half of that spacing can be made available for each of the lifters. So they can only take up half the spacing in terms of the area calculation. And again, the depth H, if the depth H, so talking about slabs here, if the depth H or even walls that you cast on the flat, if it's smaller than 1.5 times C1, you got to take that account. So like we saw last week with the concrete cone failure, taking account of all the edges can dramatically reduce the amount of area have available, and therefore give you quite a big reduction in the capacity that you have. So it's always mindful to take account of that. The characteristic resistance broken down into the formulas here. So we've got our design resistance up here with all our components. We've got our characteristic resistance, our area reduction, a whole series of factors, which I'll briefly discuss, and your partial safety factors. So your concrete and your lifting and handling. So it's 1.5 for concrete, 1.5 for your lifting and handling for concrete. Your characteristic capacity, again, there's not much in it. We've got a KV factor, which comes from the code. It's 2.3 in this case. We've got the diameter of your bar. These alpha, beta, and LF factors, they're all explained here, but they're all geometrical parameters based on edge distances, diameters of bar, effective depth. So you just crunch all those numbers, and then we've got the concrete strength in there as well. So it's when you crunch these numbers and you come to the conclusion that it's failing, the best thing to do is go back to your formulas here and just see what the parameters are. And you can see, look, obviously it makes sense. If you increase your concrete strength, you get more out of it. If you increase the diameter of the bar, you get more out of it. If you increase the embedment depth, you get more out of it as well. So it's always good to just revise what's causing the issue and where it can be improved. The next slide, yeah, it explains, look, I've got our design formula here at the top, the characteristic formula, but we've got all these other parameters, all these psi factors. Some of them are very similar to what we spoke about last week. We've got this first one, which takes into account disturbances and stresses when you're close to a corner. So it's a function of both your C1 and your C2. And again, all these formulas are kind of correction factors in a way to, based on experimental testing, to bring something that's non-linear back to a kind of a linear approach as best as possible. This psi h is a function of the depth. So basically, it means that as you decrease the depth of your slab, and as you get into less than 1.5 times your edge distance, it does not reduce linearly. So that's a correction factor for that. We've got this phi EC, which is our eccentricity factor. Again, doesn't really come into account when we're dealing with lifting designs. It's more for cast-in plates that have a number of rigidly connected bolts. This one here is an important one to take into account, and it's more so it can be your savior when you're dealing with particular designs, as the factor it allows you to gain benefit from the direction of angle of your shear force to the edge. So it's greater than 1. So it's not a reduction factor, it's more of an enhancement factor, because the answer is always greater than or equal to 1. And then we've got the 5th one here, which is the reinforcement psi factor. Depending on what your assumptions have been made, whether it's cracked or uncracked concrete, and with cracked concrete, we'd always generally have edge reinforcement in there. So it gives a little criteria there on what edge reinforcement is applicable. But you can see there's little enhancement there when you do have edge reinforcement that you can avail of once you comply with the requirements here of the code. So on the next slide, I'm just going to talk briefly about this alpha factor. So as I mentioned on the start of this failure mode, that we take C1 into account, which is the distance between your lifting pin and the edge in the direction of the force. Depending on what kind of unit you're trying to lift. For example, you'd rarely, well, not rarely, but this wouldn't be the typical situation where your shear force is pushing directly towards the edge. It might be the case, say, for example, when you're tilting, or it might be the case if you've got a manhole slab with an internal opening, and therefore the shear force is pushing towards that internal opening. More often than not, in the case of, say, again, a flat slab, your shear force is away from the edge. And if I suppose the best thing to do here is quickly, so if you've got a flat slab, and let's say this is one of 4 lifting points coming back to the center, so your shear force is generally pulling away from the edges, pulling away from the corners. When you have a shear force like this, it's going to have 2 components, one in the y-axis, one in the x-axis. So a little bit of trigonometry can work out what those values are, but conservatively, you can just take the shear force that you calculate that's going straight back to the chain hook. And using that, we have this diagram down here. This diagram down here. So it's when your shear force is parallel to the edge. And that allows you, when you work it out, it gives you a factor of 2. So it essentially doubles the resistance, the concrete shear resistance, when your shear force is parallel to the edge and not pushing towards the edge. And then if you're completely pulling away from the edge and you have no component that's going to be parallel to the edge, like up here, well, then you don't need to account for that check. So there's sometimes when you're dealing with more complex units, this can be useful gain when you do that. The final this isn't the final failure mode. This is local concrete crushing, is the next one. So very straightforward. It's one simple formula. The formula here, it's a function of the diameter of the pin and your concrete strength and your steel strength. So the larger any of the 3 of those get, the more favorable it is for you when you're carrying out this check. So it's very straightforward. And as I said, when you're doing lifting designs, you always need to include the lifting and handling factor according to CEN 15728. So there isn't too much more to be said on that one. Concrete cone failure. from last week is going to be a similar result here. So this is concrete pry-out failure, where it's like half a concrete cone. Again, same angle of 35 degrees, same critical edge distance criteria of 1.5 times the effective depth. And the failure is at the side opposite to the direction of the shear force. So as is this wedge will try and pry out. So we'll have a shear force bearing against the concrete here, and it'll try and pivot then off and kick this part up and break off. So when we look at the formula, it's getting straightforward, a few small parameters in here, and there's a distinction to be made then again, whether we've used supplementary reinforcement or not. Sometimes, and we would have in some of the factors that we saw last week, you do get penalized for having too much reinforcement in there, because the actual I suppose the wedge of concrete can't develop properly. There's disturbances to the stress path, and tests have shown that to kind of cause a reduction in strength in some cases. So there's a 0.75 factor on here when you're dealing with supplementary reinforcement. The values that you use, you take the minimum of these two values. This is essentially from your tensile failure modes last week. It's your concrete cone and your pullout. You take the minimum of those two values, and it's generally always going to be concrete cone. Pullout very rarely governs in lifting pins. So you take the minimum of those and you multiply them by this K8 factor. K8 factor, it's either 1 or 2. There's kind of no in between, and it's kind of based on the effective depth. So if you have effective depth less than 60 millimeters, which again will be rare for lifting pins, that's when it's 1. Otherwise, you use 2. Maybe if you're using flat plate lifters, you might have an effective depth less than 60. And again, when you think about it, that's one of the main reasons then why flat plate lifters always have additional reinforcement, regardless of anything else. So you're always required to have bars going across the flat plate to assist in the resistance. So that covers all the shear failure modes. I suppose, of course, all the failure modes between this week and last week in terms of steel, concrete, tension, and shear. I know I probably went a little bit quickly through that, but I am conscious of the time and what else we've to get through in this hour. So once you have all your shear failure modes and all your capacities calculated, you can then check the interaction. So if there are both tension and shear demands on the lifting pin, then the steel or concrete required to resist these demands are likely going to be the same piece of steel or concrete, and therefore you're not able to utilize the full resistance of each at the same time. So you can't have full tension capacity and full shear capacity at the same time. There's an in-between that you have to calculate, and that's where these 3 formulas come in, depending on what's the dominant failure mode. So the first formula you always look at when you're looking at the steel failures. So whatever your it's simply just utilization ratios. So it's your steel tension demand divided by your steel tension resistance squared, plus your steel shear demand divided by your steel shear resistance squared, and that all has to be less than or equal to 1. And similar one for the concrete when you're looking at the concrete failure modes. So it's your concrete demand in tension divided by your concrete resistance in tension, and the same for the shear, and that has a factor of 1.5 as opposed to 2. And then again, adding those 2 results together has to be less than or equal to 1. An interesting one here, and again, comes down to disturbance of stresses, etc. So when, say, for example, you have a concrete cone failure and you add additional reinforcement to try and resist that concrete cone failure, and then when you're looking at your shear capacities, the concrete alone is good enough. So when you have I suppose what I said here, when you use supplementary reinforcement to take up either tension or shear loads only, and the other relies on the concrete resistance alone, you got to use this formula here, and it has a small small power index up here, which does give you quite a low result at times. And the reason being is that the strain of the steel and the strain of the concrete are different. So it's not guaranteed that they'll both be engaged at exactly the same time. And therefore, one will crack first before the others. You don't get the full capacity of both. So that's quite as a more of a reduction going on here. And in summary, when you do all these numbers, when you do all these calculations, it's always advised to create a little summary table just so you can see at face value what's happening with your lifting design. So again, very suited to a spreadsheet, and you'll have this summary page then. So on the left hand side, we've all our tension failure modes, and on the right hand side, we've all our shear failure modes. And we start with the steel, so steel tension here at the top, and steel capacity or steel shear here in the top right. So the green values are the capacities, the red values are the demands. So these are just numbers just put in from a previous design I would have done. And you can see here that the steel capacity and demand divided two of them together to get utilization, you get 53%. And similar with the shear, 37.5 and 20, your utilization is also 53. You pump the two of those into this interaction formula for your tension and shear in steel, and you end up getting 56%. So the interaction check gives you slightly higher utilization than the individual tension and shear checks. You do the exact same for concrete. So we got our 4 concrete tension failure modes and our 3 concrete shear failure modes. Blowout was not required to be checked in this particular example. And we take the minimum of each of those. So that was 67 for the tension, and it was 35 for the shear. And then again, tension demand from what we would have done in lecture 1, 40 and 20 for shear, and then your utilization 60 and 57. But then we've got a larger interaction check here. So it comes down to the fact that you've got a smaller index here. So there's a bigger difference between the individual utilizations and the interaction check. But all these are less than 100%. So therefore, you've got a satisfactory design. And that's kind of a quick half-page summary of what you'd expect with a full design. These next 2 slides and 3 slides, I'm going to briefly touch on supplementary reinforcement. So if the checks on the previous slide are not satisfied, so there are a number of options available to the designer. Obviously, you can look at the concrete strength, the geometry, the placement of the lifter, etc. But we can also add extra reinforcement to supplement the failure modes. So in general, the concrete strength, the lifter position, the sequence of lifting can all be investigated. The demands and associated factors can be revisited. Are we using too high a factor? Is the weight overly conservative? Often, if you have a whole series of products that you're trying to do a design for, you pick the heaviest one and you design for the worst case. Sometimes there might be provisions to maybe do 2 or 3 different lifting designs just to break it up a bit and to be a bit more efficient. But obviously that comes with its own practical issues then as well. So we're going to discuss here 2 supplementary solutions. Concrete cone failure for tension. How can we improve the capacity if we have a concrete cone failure issue? And then in shear, it's the concrete edge failure. 2 most common ones, basically. So in the code, we're given a formula kind of like this. From the diagram, so basically you're adding steel to hold back the wedge of concrete that's trying to break out due to concrete cone failure. So typically it's going to be a series of U-bars that straddle the failure line, and you make sure you have enough anchorage both sides of the failure line. And in this example is probably the most common one is wall panels, something like that, because you're going to be severely crucified in terms of your edge distance when you do your concrete cone failure checks, and that's why this supplementary reinforcement can come in handy. So it's kind of based on a strut and tie approach, and it gives limitations on what amount of steel you can avail of. So there's a little clause in here. So if you have your effective depth, you can only, I suppose, engage the steel that's within 0.75 times the effective depth to the left and to the right. So if your effective depth is 200 millimeters, well, then you can only engage the steel that's 150 millimeters either side. So you might have to closely pack some of those U-bars. Often with a wall panel, you're going to have U-bar closers in there anyway, so you might just have to add in a few additional ones to satisfy the check. But it's a straightforward formula, again using the partial factors from before, but it's the number of bars times the area of steel times your strength of steel. So it's a straightforward check that could be used there. And then when you're doing that, because strut and tie approach, the U-bars act as your vertical ties, but you'll also need horizontal bars then for a horizontal tie. So these transverse bars. Again, they're always more than likely in there anyway from your permanent works design. So you might be able to avail of them. Here's an example here of the closely spaced situation. So in this one, you can kind of tell that 6 U-bars have been availed of. 6 U-bars, that's 12 legs. And you know, if there be 12s, you know, that's a significant amount of resistance, and you just need to make sure that the U-bars are fully anchored back into the concrete, away from the failure line. So the best way to do that is just assume that your failure line is at the bottom of your spherical head horizontal line here. So that's the point at which you need to ensure that you're full anchored. So if your anchorage is 500 mil, it's whatever your effective depth is plus full anchorage. So if your effective depth was 200, 200 plus 500, 700 is your leg length required for those U-bars. Very similar approach can be carried out for edge failure. Follows similar principles. This one here in this diagram here on the left is similar principle as the strut and tie approach, where you got your shear force, you got U-bars wrapping around, and you've got your transverse bars as well. And your U-bars basically, again, the same criteria of 0.75 times your edge distance in this case. When it was tension, it was the effective depth. So in this case, if your distance to the edge is 200 mil, well then this is going to be 150. So they're the bars that you can engage for that effect. Exact same principles in terms of the anchorage length and all that. And your formula here is the exact same. So because your U-bars are still acting in tension, the legs are still in tension. One interesting thing to note here is this K10 factor. And this K10 factor is known as an efficiency factor. So how efficient are the bars engaged? And the reason that's there is because of the diagrams here on the right-hand side, that when we're dealing with shear, for tilting, for edge distance, etc., often the common case is to put U-bars hard against the lifter to hold it back. And due to the bend radius, the radius of the lifter, the contact area is quite small, and there's always going to be a bit of concrete in there. So the efficiency factor is put in place to ensure that a safe design still exists. So essentially, when you're dealing with a supplementary reinforcement with kind of a strut and tie approach, your efficiency factor is 1. But when you're dealing with any other where steel hard contact, your efficiency factor is actually 0.5. So these are the examples given here where K10 is 1. So you've got kind of a strut and tie approach, and where K10 then is 0.5 is when you've got your steel hard in contact with U-bars, etc. And it's just because, you know, how I suppose good is that contact? Is there bits of aggregate? Is there a little air pocket just because of the different bend radiuses and the trapped getting trapped in there, bits of aggregate? And it's kind of shown that there is a reduction when tests are carried out, that you can't really avail of the full amount of steel that you put in just because of that contact area not being perfect, and therefore a little bit of movement happens, and you only need a little bit of movement to happen for the concrete to start crushing and for things to move. So on the bottom is an example of the tilting reinforcement. Some examples there where you have a kind of a crank U-bar in, I suppose, parallel to the surface. You have other ones here where you kind of crank it in such a way that it goes down the edge of the wall. And I suppose the only comment that I'd have on this is possibly to always double it up. Typically, if you don't know which way the wall panel is going to be tilted, so you only need like a U-bar in the direction to pull back the shear force. But if, for example, you have wall panels that get demolded and they're tilted up for a particular reason, for maybe finishing both sides, and then they get tilted back down again onto the truck bed, there is a possibility that it might get tilted back down onto the opposite face, and therefore the shear is in the opposite direction. So it's always good practice to add your tilting reinforcement so that it works for both faces of the concrete. That kind of covers all failure modes and all that. I won't get around to it, but I'll spend a couple of minutes just going through it. But the rest of the slides in this lecture are basically the worked example, continuing on from the example we started in the first module where we calculated the demands. It was a simple flat slab, geometry shown here, position of lifters shown, and these are the demands that we brought forward from the first lecture. So essentially, you just need to go down through the list of failure modes that need to be checked. So once you have your demand in your lifter, you can select a suitable lifting pin. So from here, we had a tension demand in the lifter of 28.1, tension demand in chain of 32.4. So you're going to be looking at a 5-ton lifter for that. Yeah, select a suitable pin. Work out what the depth of it is going to be. What did we say our slab was here? It was 250 thick was our slab. So what we have is a 180mm long lifting pin, but then because of the dome former, there's going to be this extra bit of cover here. So I think for a 5-ton, that's 15mm. So the bottom of your lifter is actually 195mm from the top. So that gives you 55mm of cover to the bottom, which is probably satisfactory. Work out your pin diameter and foot diameter because we'll need those later. So basically this just lists the calculating the tension to capacities. We've got 4 to calculate. I suppose the thing to point out here is that blowout failure. There's a clause in the code that tells you when you do and don't need to account for blowout failure. So blowout failure, if you remember, is failure of kind of the side edge of the concrete. So you've got a wall panel, you've got your lifting pin coming up here like that, and blowout failure can occur something like that where you're close to the side edge and that blows out. So there's a little clause in there, so we can ignore this failure mode if the edge distance is not less than half the embedment. So in this particular example, I think our edge distance was 350 and half the embedment was 97.5, so nearly 100mm. So the 350 is not less than 100, and therefore you don't need to check that. Pull together all your inputs, your concrete strength you're using, your partial factors, have those all kind of as on the side of your page, so you can always refer to them. And again, these lifting and handling factors always need to be accounted for. Anything else worth noting here? Yeah, so this is essentially just repeating the slides that we would have shown already, but then in blue, I've added the actual numbers for this particular worked example. So you can follow through the whole design for this. working out, wondering how the area comes together, all these other factors that we only briefly discussed on. For concrete cone, we came up with a value of 101 kilonewtons for that. Concrete pull-out failure, again, like I said, you'll always find that this rarely governs. When you work through the numbers, you get 220 kilonewtons. Concrete splitting failure, we can work out what the lifting is, and again, it's not shown here, but that there should be 2.07, like we discussed at the start of this lecture. But you can see in this particular example, there's a 5-ton lifter, so you actually need 2 B8s. So you're more than likely going to have more than that in the vicinity of the lifter anyway. So again, this failure mode rarely governs. Concrete edge failure, so shear failure modes are moved on to then, and you can see here where I was explaining that you've got the component of shear parallel to the edge. So you're typically pulling away from the edges, but there's going to be a component parallel to the edge, so you can utilize that factor of 2 when you get to the factors. Explaining the edges, so when we get to this, yeah, we got this factor of 2 that we can avail of. So when you crunch all these numbers, you can put them all into your final formula for shear edge failure, and you get 92 kilonewtons in shear. Concrete crushing, again, a simple formula. This one seems to govern quite a bit, 26.3 kilonewtons. And pry-out failure, again, pulling from the minimum of our concrete cone and pull out, we get 2 times the 229 divided by your partial factors, you get 203. So, and then the last thing to do is check your interaction formulas. So because we weren't utilizing supplementary reinforcement, we didn't need to use this formula down here. So we just need to use the shear interaction check and the concrete interaction check. And then finally, I have the slide, which summarizes all the values that have been used in lectures 1, 2, and 3 for this particular worked example. And you can see here, so we can work down through our tension failure modes and shear failure modes for the steel lifting pin, 56 and 65, and then our interaction is 74. And then our concrete cone failure modes, 28, 62, and then your interaction is 64. Generally, what you might find is for typical slabs is that the pin might be the governing failure, so the steel. So you can see here that's the highest utilized, 74. But when you're dealing with walls or units with openings, it's generally going to be the concrete. So when you have no issues with edge distance, you can generally utilize the full capacity of the concrete, and therefore the steel will be the failure mode. But when you have any disturbances, you're generally going to be caught with the concrete failure modes. So I think in lecture 5, the intent is to go through a couple of examples. So lecture 5 is purely going to be worked examples. So I know I went through this one fast. I was conscious of time, but yeah, in 2 weeks' time we'll go through a few more worked examples, a bit slower, so it'll be easier. And also, this was probably a bit too simple of a worked example, so we'll do a few more got to do with tilting and stuff like that in 2 weeks' time. Next week we're going to kind of diverge from this lifting pins, and we're going to look at strand and rebar lifters. So we'll call it there, and if anyone has any questions, please feel free to ask.